Yeah. Okay.
I'm not too pressed about it. I don't really care that much about it.
Yeah. I can just watch.
I've got to record it anyway, so it's gonna like this last part's pretty self-explanatory. It's all bio. It is like literally all bio. I'm not gonna lie. Like the whole thing is just biology.
Oh, okay. Okay.
Oh yeah, no, no,
What
actually,
about
yeah, no,
homework?
that's a lie. That's a lie. A little bit about the Zwitter ions, but we'll deal with them when we
Oh
get to
yeah,
them.
you did talk about that.
Yeah, I discussed them briefly. We're gonna talk about them more. I'm gonna talk about them a little bit more. So we'll have. Let me just bring up these slides, and let's get started.
Okay.
So, everything's working. Recording working perfect. Okay. So, uh, we talked about this activation curve already, yeah, and we talked about how the temperature affects the function of the catalyst, right? Eventually, right, if it's too low in temperature, it's going to deactivate. If it's too high in temperature, it's going to denature, right? And it denatures because the tertiary, the secondary, tertiary, and quaternary structures break down, right? They break down
Yeah.
because they're made of like the hydrogen bonds. They're made up of dispersion forces, dipole-dipole, disulfide interactions, ionic bonds. All those things are going to break down, right? So
Yeah.
we just move on from here, right? It says when a catalyst is heated to 75 degrees, the part of the enzyme structure that will be least affected is what will be least affected?
D.
What's least affected? Because that's what's most affected.
Oh, like A.
A, like if you think about it logically, the primary structure of this one is made up of covalent bonds, and these covalent bonds are really really strong. Yeah, you have to heat them up a
Yeah.
lot. So this is like because this is the
Yeah.
remember this is what the backbone looks like. Yeah, so I'll just draw these out. Yeah, so this is what the backbone looks like. And here's our R group. Here's the R group. Oh yeah, here's the R group over here. Yeah, these very strong covalent bonds. They're very hard to overcome. So we don't have to worry
Mhm.
about the primary structure breaking. It's more that the folding, like the folding of the actual thing stuffs up. Yeah.
Mhm.
So an enzyme is denatured at low temperatures, is consumed in reaction, is always active, is always specific to a certain substrate. Is that true? Which one of these is true?
D.
D. Yeah. No, it deactivates under low temperatures. It's never consumed. Catalysts are never consumed, and it's not always active. So here's the idea of the Zwitter ion. Yeah. So as I said before, Zwitter ions are for so we have three types of amino acids that we need to deal with in the VC. We have the basic amino acid, we have the acidic amino acid, and we have the neutral amino acids, right? And with the neutral amino acids form Zwitter ions, right? So I'll bring up the VC data book to demonstrate my point a little bit further because I feel like the data having the data book there will show it off nicely. So let me just pull up the data book. So let me just switch over to the VC data book. Yeah.
Ugh.
Oh, but what was that?
Oh, I'm tired, bro.
Yeah, no, fair enough. I've like slept like fuck all day.
Yeah.
So
I'm just on the bed right now.
the the so basically, right? Any so a neutral amino acid just constitutes is anything that doesn't have an NH2 or a C or like a it doesn't have an amine group. So an amine group, which is just the NH2, right? Or a carboxyl group, right? Which is the C double bond O, right? And a neutral amino acid won't have these. So alanine is a neutral amino acid, right?
Yeah.
Wait, no, no, let me see if I can find another one. Cytosine is another neutral amino acid, Over here we have isoleucine and leucine are both neutral. So yeah, do you see how it's just all the ones that don't have that acidic bond? Yeah. So it's
Yeah.
either the ones that don't
Yes.
have the amino acid on their residual chain, right? It's about the residual
Mm-hmm.
chain. We don't want it to be on the residual chain, yeah? And I'll explain what happens on the residual chain. But first, yeah, this, like, let's take alanine, yeah? Which is our neutral amino
Yeah.
acid. And in neutral conditions, right, in a pH of 7, it's gonna look like this, yeah? This is what it's gonna look like.
Yep.
So it's gonna look like this. Where the carboxyl group donates a hydrogen and the amine group actually accept a hydrogen because they're acid. This is a base. This is an acid, and this is base. Yeah.
Can you repeat the last bit? My like computer lagged out.
Yeah, that's all good. So if we like if it's in acidic conditions, what's gonna happen is the Zwitter ion for alanine is gonna look like this. In neutral, I mean in acidic conditions, so in a pH less than 7, yeah? And why is this the case, right? It's because the Zwitter ion acts as a base, right? It's trying to lower the pH. That's what it's trying to do. And that's why it's accepting H pluses, yeah? But it's not donating them.
Okay.
So it's acting as a base. That's what you want to think about. It's acting as a base, right? So here it's only accepting. And then when it's above 7, so it's greater than 7, yeah? It's doing the opposite. It's acting as an acid. So over here, if I remove this, shit, my pen's been acting up. Here, it's acting as an acid. Yeah. So
Okay.
that's what's happening with the Zwitter ion. Yeah, at the neutral pH, at a pH below 7, and a pH above 7. Below 7, it acts as a base to lower the pH. I mean, to increase the pH back to a neutral condition. Yeah. In the higher pHs, it acts as an acid to lower the pH. Yeah.
Yeah.
Does that make sense?
Yeah.
The big thing that you want to focus on here is just like how the pH affects the amino acid. Yeah. So now, so the big thing that you want to remember here is that the Zwitter ion is what it looks like at the neutral pH. Yeah. The Zwitter ion
Yeah.
is what it looks like at the neutral pH. The other ones aren't the Zwitter ion anymore. Zwitter ions are defined as having an overall neutral charge, but highly ionic polar regions. Yeah.
Okay.
Does that make sense?
Yeah.
So think about how think about how the bonding between different alanines would be affected if at different pHs. Because here, right, we have this plus over here, right? If it wasn't a plus, and let's just say it was the regular alanine, right? That produces different bonds than the basic version of the alanine, correct?
Yeah.
Because like one would form those ionic interactions, the other one could only form hydrogen bonds, and hydrogen bonds are very different from ionic interactions. Does that make sense?
Yeah.
Now the big thing
It's
that
just
we
a lot to complete.
yeah,
It's just a lot to take. Yeah.
yeah, no, that's all good, that's all good. So because the main point of this is just to get you familiar with it, because you don't just like walk into chemistry and you're like, holy shit, there's so much stuff, right? It's more
Yeah.
that it's just like it's chiller. So
Okay.
the for example, if we had asparagine, yeah, asparagine is a it won't form a Zwitter ion, as I said before, because it has a amino group over here. Yeah, it has an amino
Hmm.
group on its residual chain. Yeah. So
Yeah.
here, right, if this one is in if this one's in acidic conditions, right? If this one's in acidic conditions, this is what it's going to form. So it's going to form the regular backbone plus this over here. This is what it's going to form. Yeah. And do you
Okay.
see how, like, because it's acting as a base, remember? It's accepting ions, but it's not donating. Yeah.
Yeah.
Do you see how, remember how the tertiary and the quaternary structure were affected by what was in the residual chains or the R group?
Yeah.
Do you see how might affect the folding, yeah, of our amino acid?
No.
So like because here this can produce an ionic bond now, yeah? This won't produce our
Yeah.
regular dispersion or hydrogen bond, yeah?
Yeah. Oh, okay.
So here
It's basically like that.
it's producing different intermolecular forces, right? Which means that the amino acid that we have that might work in neutral conditions might not work in acidic conditions because it has different bonding, which means it won't fold correctly. Yeah? That's the
Mm.
thing I want to highlight here. If we had, let's just say, the aspartic acid in basic conditions, it's going to look like this. Yeah? Uh, H, wait, no. In basic conditions, so it's going to act as an acid. So we have it 2, and we have a COOH, and we have a CH. Remove that one. Right. So that's what aspartic acid is going to look like under basic conditions, yeah? So here, if the pH
Yeah.
of this is too low, we're going to have the folding of our tertiary and quaternary structure being affected here. And we don't
Mm.
want that to
Okay.
happen. We don't want the bonding to,
Yeah.
to stuff up because like think about it, if we have a misfolded protein, it's going to cause a lot of problems.
Yeah. Cause like cancer and all that.
Yeah. Will cause us
What's
cancer,
different?
can cause a whole bunch of diseases.
Yeah, we don't want any of that.
So that's where the amino acid structure will depend on the pH of the actual solution. Yeah, and specific amino
Mm.
acids won't be able to form Zwitter ions, but they will form cations and anions, which will affect the overall structure. Yeah.
Mm. Okay.
So here I'm just like I had this one over here to point out what happens when the pH of aspartic acid is very high. Yeah. So this is what would happen if the pH is very high
Okay.
because it's acting as an acid, it's donating its H. Yeah.
Yep.
And over here you have lysine, right? And lysine, this is what's happening in a lower pH where it's acting as a base. So it's accepting those H's. Yeah. So over here and over here.
Okay.
So yeah, the big thing is that you want to remember that the pH will affect the bonding. It will affect the primary, secondary, and tertiary structure, as I said before, right? It forms different interactions between the substrate and the substrate complex. Again, because remember the bonding between like when we talk about specific and complementary, specific refers to the bonding being specific. Yeah, if the bonding
Yeah.
isn't specific, yeah, then the enzyme and the enzyme substrate can't, I mean, the enzyme and the substrate can't come together to form that enzyme substrate complex.
Yeah.
Yeah, and then it also changes the charges of the side chain. We've already talked about that. So here, right, the structure of the following amino acid asparagine is shown. Draw the structural formula of asparagine at a pH of 1.0. So, what is it acting as? Is it acting as an acid or a base at this pH?
A bit. And then Acid?
It's acting as an. It's not acting as an acid. It acts as a.
Base. Base.
Yeah, it's acting as a base. Yeah, it's
Yeah.
acting as a
That.
base to lower the pH. It acts as a base to lower the pH. So here, what's going to happen is that it's going to have an extra H. It's going to have a plus. It's going to have an extra H over here. It's going to have an extra plus, and that's what it's going to look like.
That's because it's below pH of 7.
Yeah.
Yeah, okay.
So here, met and calpaphyllene is a small protein found in the nervous system and the gastrointestinal tract of the body. Which one of the following are correct about the structures of the two terminal ends of the met and capel? I don't know how to say that. At a very low pH. So what's happening to this thing at a very low pH? What does it act as?
Like a base?
It acts as a base. So what is it going to be? A, B, C, or D?
Um, like D?
Yeah,
Or yeah,
it's going to be D.
it's is it D?
Yeah, it's D.
Oh, okay, okay.
And then here, which one of the following statements is incorrect regarding enzymes? Enzyme activity differs with a temperature change. Enzymes are biological catalysts. Enzymes are consumed in reactions. Enzymes differ with a change of pH.
C?
See,
Yeah.
the
Oh, this is
follow
pretty bad.
yeah, the following structure is an example of a tertiary structure, quaternary structure, as with ion or protein.
D?
D,
C.
C, C. I was like D, but
No, I'm not that retarded, bro.
okay. So, uh, this is just describing how a competitive enzyme inhibitor works. So,
Yeah,
I know you already know this, but for the sake of the recording, I'm going to explain it anyway. Yeah?
yeah, not.
We have, this is what regularly happens, right? A substrate goes into the enzyme and forms a substrate complex, and then afterwards it releases whatever the product is. Yeah? Now,
Yeah,
sometimes whatever it releases could be bad for us. Yeah? So what we sometimes do is we use competitive enzyme inhibitors. Essentially, they block up the active site of the enzyme uh, in order for this substrate to not be able to bind and form this potentially dangerous product. That's the whole point. Yeah.
yeah. Okay. Yeah, yeah,
So there's nothing too crazy. We
yeah.
also
Obvious.
have non-competitive enzyme inhibitors, but the VC the textbook doesn't discuss it, and I don't think it's on the chemistry study design. But a non-competitive enzyme inhibitor essentially it attaches to the outside of the enzyme, and it changes the shape of that enzyme. It changes the shape of that active site. So now it's not specific anymore. So that's non-competitive enzyme inhibitors.
Is that like the what was it, allosteric site
Yeah, yeah,
deadeners? Or,
it's the allosteric side.
do,
If you want to get all fancy with it, yeah, it's the allosteric side.
do we need to know that, or do we just
No,
it's
no, no.
just
You just need to know that it bonds to the outside. You don't need to know about the allosteric side.
yeah,
But I don't think they ask about it. They care more about the competitive ones. So, yeah, here this is a common reason why Alzheimer's disease is a big issue. So here, this reaction is a big issue because essentially breaks down this thing that we need in our body. Yeah.
yeah,
So what we do is, oh yeah, this is basically the whole bonding, right? How it's specific, right? The bonding is specific. Yeah. I just want you
mhm,
to remember that the bonding is specific. Yeah.
mhm,
Now, this is our competitive enzyme inhibitor, which stops this reaction from occurring. Yeah. It blocks it up. It's competitive. Yeah. So it
yeah,
basically stops it from it just stops the breakdown of this thing, right? Which essentially reduces the effect of Alzheimer's disease, or is supposedly reduces the effect of Alzheimer's disease. So,
okay,
enzyme inhibitors work by increasing the activation energy, decreasing the activation energy, binding to the active site, creating a second active site.
See,
C. C.
and
And that's the end. So,
can I leave?
yeah, basically you can leave. That's all for chemistry, guys. Ba-da-ba-ba.